Welcome back. In this video we're going to continue our introduction to R3 by defining this set and looking at our first graphical interpretation of ordered triplets. We start by defining this set as the set of ordered triplets such that each coordinate of these ordered triplets is a real number. The way we read this mathematical statement is R3, you can think about this as 3 copies of the real numbers, equals the set of, this first open curly bracket is called set notation, and you can read it as the set of ordered triplets, where each ordered triplet is given as an x, y, z. These semicolons you can read as such that each of the coordinates is a real number. When we think about the word ordered triplets, we refer to each coordinate based on its order while reading left to right. And what we mean by this is when we look at x, y, z, this ordered triplet has 3 coordinates. The first one on the left we call the first coordinate. The one in the middle we call second coordinate. Could you guess what we call the last one? Ding, 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 ding. You got it. The third coordinate. This is important because depending on which order you write it, it has a very different structure. And an example of this, the system, the point 1, 0, 0 is definitely not equal to 0, 1, 0. Here the first coordinate value is 1, the second coordinate value is 0, third coordinate value is 0. Here the first coordinate value is 0 and the second coordinate value is 1. Those are different points because they're ordered. What's really interesting about this is just as we graphed ordered pairs on the set of 2 axes called the Cartesian plane, we can also graph ordered triplets on the intersection of 3 axes. These are 3-dimensional graphs. Yay, how exciting to get to that next level. When we go to graph an ordered triplet, we need to create 3 orthogonal axes that intersect as an origin. The word orthogonal is a higher dimensional version of the word parallel. You can think, perpendicular. You can think about these as perpendicular. It's just a fancy way to say perpendicular when you're not in a plane. When we do this, we assume a convention that's called the right-hand rule. And the right-hand rule assumes the following. First, I draw my x and y axis. I'm going to do something a little interesting. I'm going to draw my positive x axis going off to the left here. And I'm going to assume that the 0 point on my x axis is right where the solid line meets the dotted line. So here's a little bit of tick marks. Maybe this is 1, 2, 3, 4 off in the positive direction. Here's my negative axis and my x. I'm going to assume that my y axis comes straight up out of the piece of paper towards the viewer. But in this situation, I'm going to draw that slightly off to an angle. So you have to pretend that this black line is coming straight up out of the board towards the viewer. And I'll call this the positive y-axis. Right here we'll call 0. And then the negative y-axis goes off in the opposite direction, obviously. Here we'll do the same tick marks. Here's those tick marks, maybe 1, 2, 3, 4, coming up out this way. The right-hand rule says the following. If, as I'm drawing the graphs in R3, I take my right hand, this is my right hand, and I point the index finger of my right hand in the positive x direction. I take my middle finger 90 degrees and point it in the positive y direction. Then if I take my thumb and I draw it orthogonal to both of those, so up in this direction, my thumb will point in the positive z direction. So in this case, if I'm wondering how do I draw the positive z, index finger in positive x, middle finger positive y coming straight up out of the board, thumb orthogonal to both of them. Oh my God, I see immediately that by the right-hand rule, my positive z direction should be 90 degrees to both of those, coming straight up this way. So this would be the positive z. And then the negative z would obviously come down right under this. So here's z negative, and we can write the tick marks here. And to make it super clear that these are all orthogonal, here the z-axis is orthogonal to this, the z-axis is orthogonal to this, and then notice that the y and the x-axis are orthogonal. This is a 3-dimensional graph represented on a 2-dimensional piece of paper. This point right in the center we call the origin because it represents the 0 on all 3 axes, 0x, 0y, 0z. What's really interesting about this is we might start to graph different sub-images on these 3 axes. What would happen if you set z equal to 0? What geometric object would you get? What would happen if you set y equals 0? What object would you get? Etc. In the next video, we'll start talking about these very famous objects, and we'll make some analogies between R3, the graphs of 3-ordered triplets, and R2, the graphs of ordered pairs. I'll see you in the next video.